Welcome to Mathematics and Statistics. Today we'll be starting with linear programming. This is the chapter 6 of your part 2 class 12 and this is the first part of series Mastering with PYK. Start with the concepts. Now what do you mean by linear programming? So let's start with definition. So a linear programming is a technique or a concept. Right? So it is a concept or a technique for finding an optimum solution. Optimum solution can be minimizing something or maximizing something depending on the linear objective function, wherein we will have certain restrictions or constraints or boundary with two or more variables. So again, linear programming, which we also write it as LP. So linear programming is a technique of finding an optimum solution, because in life we need to find out the optimum solution which can either minimize my cost or maximize my profit. Example, and to a linear objective function, that what am I trying to achieve, right, with certain constraints. So that is my boundary conditions or my limitations, right? So my limits have to be kept in mind while designing a linear program. And how we will be doing it? By using two or more variables. A real life situation will always have more than two variables. Okay, so we will have to work on these parameters and come to an optimum solution. Here in our syllabus, we will be only working on two variable concepts. So we are restricting all our questions on the two variables. And also the decision variables, meaning the optimum solution will be designed or derived for only non-negative quantities. We will be not discussing about any quantity which is negative. So let's go ahead. Now, we understood what is a linear programming. We'll be needing a technique. We'll be needing an optimum solution for which we should have a linear objective function. There will be certain boundaries and two or more variables. Now, so from definition, objective linear function is denoted as z or z is equal to ax plus by, where x and y are my variables, right, and b and y are my subject or the quantities which we have to find out. Minimum and the maximum solution, right? It can be it is also known as optimum solution, right? You cannot have minimum and maximum simultaneously. It will be minimum or maximum. So example, when I need to maximize something. So maximize like profit, sales, production or manufacturing. Simultaneously need to minimize something. So minimize like the cost of production, right? The wastage. While producing something, I need to minimize the wastage of my material. We also need to minimize the travel route. So your Google Maps, your route maps, travel time, right? So that is the optimum solution. So restrictions would be something wherein we'll be only talking about the non-negative values. So my x and y, meaning example, the variables would be always greater than or equal to 0, meaning they can be 0, but they will be not negative. Right? The variables we know as x, y, z, anything. Once we have to find out a optimal solution. Optimal solution is also represented or referred as a feasible solution. So what is a feasible solution? So feasible solution would be any point in a region, feasible region, that gives the optimum value. So depending upon the region of operation, right? So if this is my region of operation, I will have say x and then there will be something like y. So assuming this is my region of operation. So in this region of operation, I will have a value which will give me a maximum or a minimum value. Say this point gives me a minimum value, right? There will be a point. So there will be x and y values associated with it, right? So coming back, so optimum or a feasible solution means any point which will give me that optimum value to an objective function. So objective function would be, what do I need to find out, right? It will be minimum or a maximum is called as a optimum solution or a feasible solution. So at the end of this session, what we would learn? We would be learning how to formulate a linear equation, what is an objective function, optimization of a problem, feasible region and the feasible solution, right? So we know by definition what is the linear equation, what is the objective function, right? Optimization of the problem would depend on whether I need to maximize, right? I need to maximize or minimize. So that will depend on the requirement. Feasible region can be the entire region which is feasible, but a feasible solution will always be an optimum solution which will give me the maximum or the minimum value, right? So we'll start this chapter by going through the examples. So this is an example. A dealer wishes to purchase a number of fans and swing machines. So here is a dealer who has to purchase fans and swing machines, right? So we have two fans and swing machine. He has only 5,760 to invest. So this is what your restriction. So he cannot spend beyond 5,760 and also has a space for at the most 20 items. So this is again a second restriction. So he has a first restriction which talks about the money. Second restriction talks about the space. A fan costs to him as rupees 360. So this is again a condition wherein he cannot cross or get a fan less than 360 rupees. A sewing machine would cost him 240 rupees, right? He expects to sell a fan at a profit. So now he needs to, his objective is to maximize a profit. So selling a fan at 22 profit, meaning over and above the selling price, he should be able to gain 22 rupees. And a swing machine for a profit of rupees 18, right? So this is his objective. His objective is to maximize the profit. Assuming he can sell all the items that he buys, how should he invest his money to maximize his profit, right? So his investment is a boundary condition, space is a boundary condition, cost is a boundary condition, and these two are his objective, right? So we have to express this as LPP, that is linear programming problem. So let's start. So solution, we define the linear equation or a linear program as minimum or maximum solution or a optimum solution. So here we are going to find out the maximum solution, which is our optimum solution, because we have to maximize the profit. Linear objective function is, that is Z, that is to maximize by selling the fans and the swing machine. Restrictions, we have 4 restrictions. We have an investment as a restriction, we have the space as a restriction, we have a cost of fan as a restriction, we have the swing machine as a restriction. And the variables which we have only 2 variables, and anyways we are going to do about only 2 variable problems. So we have variable as fan and swing machine, right? So let's proceed. So variable fan, say X, denoted by X, and swing machine, say denoted by Y, right? So we have X as a variable and Y as a variable. Now constraints, we had 4 constraints. One was the amount of investment, second was the space, and at the same time the cost of the fan is available at 360 and a cost at which the sewing machine is available is 240 rupees. Optimum solution, we need to maximize profit, and the expectation of the dealer is profit from the fan should be rupees 22 and the profit from the sewing machine should be rupees 18, right? So let's see how we can use these given facts to arrive at the LPP. Okay, so linear equation or a linear program, variable can be 0 but cannot be negative. This means the fans purchased by him, because of the limitation of 20 space, he may purchase fans as 0 or sewing machine as 0, right? So here the variable, which is the fan and the sewing machine, can be 0 but cannot be negative. Also, we are not dealing with any non-negative problems in this syllabus. So say fan, we said x, so fan would be always greater than or equal to 0. Sewing machine y, which will be greater than or equal to 0. Constraint, amount to invest, right? So we know that the cost of a fan is 360. So if we purchase x fans, so it will be 360 multiplied by x plus 240 multiplied by y, that is the sewing machines. It should not cross the investment of 5760. This means it can be equal to and less but not beyond 5760. The second constraint is the space. So space is to place number of fans and the number of sewing machines should be always less than or equal to 20, because beyond that the space is a constraint. And the optimum solution here is to maximize the profit. So how do we write the equation? Say Z will be, I need a profit of, the dealer's expectation of the profit is 22 from the fan and 18 by selling the sewing machine. So we have three equations. One which talks about the constraint with respect to the investment. Second with respect to the space. And the third one is the optimum solution, right? Now we are not going to solve these examples. We are just going to understand how do we interpret and write the equations. Solving is easy. Solving can be done at the faster pace. But understanding and the given facts and delivering it in the linear equation is more important. So what do you mean by feasible region? It is a set of points which satisfy all restrictions, right? So in the previous question, so the restriction was that x, that is fan, plus the sewing machine, right? The space was less than or equal to 20, right? So we will go with less than or equal to 20. So what are the possible solutions? So what can be the possible solutions? So F can be, first solution we can write it as, the first solution can be 4 fans, 16 sewing machines, right? Or vice versa, or it can be say 3 plus 7, right? It can be any number. So these are all possible solutions. It can be 1 plus 19, right? It can be 20 plus 0, right? So there are number of solutions which are possible. So these are the set of points which will satisfy any of our condition. So these are known as feasible region. This is known as feasible region. So what would be a feasible solution or an optimal solution? So again in the previous example we had fan plus sewing machine. the space is less than or equal to 20. So any point on the feasible region, okay, that will give me maximum or a minimum value to the objective function is called as a feasible solution. So how we will be arriving it? So we will be arriving by putting the value in the optimal solution, that is z is equal to ax plus by, and try to get the maximum or a minimum depending on this situation to get the optimal solution. Right? So far so good. So see you in the next part. Keep practicing. Remember words of Abraham Lincoln. He once said, I am a success today because I had a friend who believed in me and I didn't have the heart to let him down. So be your own friend. Have trust. Keep practicing. Practice hard. Bye bye. All the best.